Okay, so today I'm going to teach you about scanning tunneling microscopy as well as atomic force microscopy. Uh, and scanning tunneling microscopy got the Nobel Prize of 1986. It was shared with the electron microscopy by Ernest Ruska. And now question arises that where did the original idea of creating a better microscope come from? And the story behind birth of STM and AFM. Of course, humans wanted to see the atoms. Please remember, till this moment, till the birth of STM, nobody saw, nobody had direct images of atom. The atom was just indirect observation through the scattering experiment. The theory of atoms were available. Everybody believed the atoms uh, are, the atom is theory, and we had quite well developed periodic table. Physics was at a very advanced stage. Biology was fairly moving. Chemistry was also in good hands. But nobody had a clear understanding of surface chemistry of atomic arrangement of surfaces. No other microscope till date had any clear image of atoms. So please remember the complexity of the challenges of the technology. Yes, the idea was there, and people were fascinated by the idea given by Richard Feynman, who had already given a thought that whether it is possible. It was like a challenge to physicists that whether it is possible to move atoms, it is possible to create machines at nanoscale. Can you arrange atoms one by one? So that is not easy. I mean, if you want to be able to move atom by atom, first you should be able to see the atoms. Even if you see the atoms, it is not guaranteed that you can manipulate them. You can move them the way you want. Can you make molecular motors? So that was a very far-fetched dream, and he wanted to make memories based on quantum computing. Actually, what we have not even reached there. Feynman had basically thought about computing way back when the quantum mechanics, people started believing quantum mechanics, and it was already well uh, I mean, it was acceptability was quite low. So STM not only proved his one of his dreams, that it was able to give a clear, very high resolution image of atomic surfaces. Second thing, scanning tunneling microscopy was first time it was able to realize his second dream, that it is possible to move atom by atom. So then IBM people, they made quantum coral. I'll show the image. Uh, okay, at ultra low temperature. So third thing was information storage, whether you can store more and more information at nanoscale, even lower than that. So the concept of nanotechnology is credited because, see, technology, something becomes technology when it is useful. So how will you use a few thousands of atoms? You should be able to use few thousands of atoms when you can control the uh, assembly process of few atoms. You are able to look at the physical properties of those thousands of atoms, and you can make them over and over again. Then only, and you find some useful properties. Then only that uh, uh, usefulness of technology comes. Otherwise, technology cannot come if you do not have, if you don't fulfill these conditions. Finally, there was also a roadblock that uh, as far as I understand, that there was no direct. There were other lot of proofs for quantum mechanics, and yeah. So, but STM gave a very good proof, experimental proof of quantum physics. the tunneling process, right? So it was a first demonstration, one of the first demonstration, perhaps, I'm not sure, but it was a clear-cut demonstration that electron tunneling does take place. I'm not sure about any similar experiment. I'm not sure. I think quantum tunneling experiments people were doing, but there was no technology out of that. Yes. Uh, So let us move forward. So he shared the idea. As I mentioned, you can read about that. And one of the possibility was to arrange the atoms the way we want. Can we do chemical synthesis by mechanical manipulation? Uh, so first, we need a better microscope that can also move the atoms. So microscope means it should be able to visualize. Uh, okay, not then only you can start thinking about moving atoms. So at IBM Zurich, Switzerland, two scientists, Binning and Rohrer, finally declared, they filed patent in 79. They said that, yes, we have a microscope which can image surfaces at the atomic resolution. And that was mind-boggling, believe me. That was the first atomic uh, resolution image, any microscope. It was a big milestone for humankind, actually. It was like, if you were in that time, it was a great excitement. And that is the reason within 5 years, this invention got Nobel Prize in physics, which is not very easy, right? So on the other hand, Riska had invented electron microscope, another physicist at Siemens. It's a very famous company, even it exists even today for medical tools, medical physics mostly. So he had developed electron microscope in 1939, which could see information down to few nanometers, right? Uh, and in 1986 only, after almost 50 years, Riska shared half of the Nobel Prize with Wiening and Rohrer. So what was the problem? That electron microscopy didn't excite physicists that much. So I'll come to that answer in a minute. Electron microscopy does excite interest in almost all the scientists today, but it was not the case since till 90s actually. I'll tell you the reason. I think you know the reason already. I've taught this already. So this is the picture of Ernest Ruska. So he didn't look like this when he invented the microscope. So that is the case with most of the Nobel Prize winners. So when the discovery happens, they never look like crazy old professor. They were quite young looking, but by the time they get Nobel Prize, they are already quite old. So this is the actual photograph taken, of these two inventors, Gerd Bedig and Heinrich Rohrer. They shared quarter of the prize along with Professor Reska. So Reska got the Nobel Prize for work in the electron optics and the design of first electron microscope. And please note that these two people got the Nobel Prize for scanning tunneling microscope, not for the atomic force microscope. Okay, even though one of them later invented atomic force microscope as well. So let us move to the story, how these two people landed up in this kind of research, what motivated them, and that make science interesting. Otherwise, it connects actually our own thoughts also. So, was it serendipity that, okay, one out of the blue, they just thought, okay, let me go to the lab and boom, there is a scanning tunneling microscope. Does it happen like this? Or there was a incremental improvement over the technique? Yes, there was incremental improvement over the technique, and that's what I'm going to show you. That it was not like a boom, okay, abracadabra, and suddenly you have STM sitting uh, at your desk, and you are, the way it is shown in the movies. The scientists are shown in the movies, okay, that they mix in some chemicals and with a white coat and crazy hair. Okay, so there were some predecessors of STM, and there were two predecessors, very important discoveries, but they were not able to go to that resolution as STM was able to provide. But they were very important invention actually. That's why I thought that I should put those inventions here. One of the first invention was topography basically, the instrument which can give the topography. So that's why it was named as topographiner. It was invented in 1972. Okay, almost 50 years back. And so you have basically a concept there that you can move a needle and you can measure the topography. The concept was there, fine. Second concept you need, so you basically you will be able to raster scan uh, the tip onto some surface. Second concept you need is tunneling. Concept of tunneling was already there in the PhD thesis of Diode in 1978. So that I told you that it is related to quantum mechanics, exponential decay of tunneling current. Uh, so I would like to spend some time on this important invention, which was done almost 10 years earlier than scanning tunneling microscope. So in this experiment, these two scientists, or rather three scientists, Young, Ward, and Scary, they were able to image the surfaces by using a metallic tip and scanning it almost 100 nanometer above the sample surface. Please note that 100 nanometer is quite a large distance for tunneling experiments. People who study quantum chemistry or quantum physics, they know that 100 nanometer is, you can't have any tunneling taking place. 100 nanometer is a big distance. Even for the forces, van der Waals forces dies around 10 nanometer. 100 nanometer is a big distance. So how could they get the current flying the tip such a large distance? So answer lies in the field emission. Field emission, all of you know because you have taken the electron microscopy course. Yes. Any question? Mima, any question? Okay. Uh, so okay. So field emission, basically they applied very strong field. In this case, field was quite high. You can see kilo electron volt. Kilo electron volt, you know that already having experienced electron microscopy, that kilo electron volt is not a joke actually. It's quite high. And then they were able to look at the surface resolution, surface images with the resolution of 400 nanometer, which was not a big deal because TM could already give you much better in a few nanometer at that time. And so, but it was important discovery. It was important. So this was basically a precursor, important precursor, very important precursor that this has many technologies which could be used in STM actually. Many technologies. So, for example, uh, moving the tape, applying the voltage and all kinds of things. So this is the image which people got using topographer, using field emission. So then finally, probably they were able to improve the resolution down to 20 nanometer, and the bias voltage was also uh, uh, lower, and Z resolution was quite good, 3 nanometer, but was not enough. And second predecessor was takes except PhD thesis in 1978. He was able to demonstrate. Yes, this was the first experiment to demonstrate the vacuum tunneling, that electron can tunnel between two electrodes. In this case, the electrodes were made of gold, and so that's what you do in scanning tunneling microscope. But Teague apparatus allowed fine adjustment of gap width, but didn't have raster scan. So obviously you can't do tunneling at large distances. That means this guy was able to see. Please remember, in tunneling experiment, you have to bring two surfaces quite close to each other. In like less than 1 nanometer. So if you have that control, it's not joke to bring two objects at that distance without crashing them to each other. So it requires fair amount of electronics and piezo raster scanning and other things. So again, important piece of technology was required, but he didn't do raster scanning here. But in this experiment, they did raster scanning, right? One technology here, raster scanning. You can see that these piezo tubes and other things are there. Okay, you could move the tip over some surface. You could get the image. These are the current images, the current maps. Similar images STM also gives you. Nothing better, nothing more than that. But resolution is far better because you are using this technology rather than this physics rather than field emission physics. Please note that. So it's a tunneling which actually brings down the resolution like anything. So that was the birth of STM, which was mind-boggling at that time. It was unthinkable. Probably the excitement would have been really a lot. So you can see that this was a successful collaboration between two physicists at IBM Zurich. And this collaboration started in 1970s, and finally it gave birth to STM in 1981. And one of the first objects they were able to demonstrate in front of the world was a silicon surface. Obviously, it is one of the chosen surfaces for physicists, silicon 111. And they were able to show 7x7 superstructure. Okay, so there is a surface reconstruction that takes place. I hope you are aware of surface reconstruction. Catalysis people, they know more about that because that directly affects the catalytic properties. So last few surface atomic layer, they undergo a tremendous change to reduce their surface energy. And one of the ways the surface energy is reduced is, either you can grow more atoms to reduce the surface energy, so that surface growth takes place, or second one is that basically surface atoms, they undergo a certain rearrangement. And in this case, it is 7x7 superstructure. For example, if you take XRD or glancing angle extra diffraction, then you will be able to pick up some extra diffraction peak. So they wanted to study superconductivity, and they wanted to look at the electronic structure, and that was a driving force, that they were superconductivity people, and no existing technology was so basically they were looking at the resistivity. Physicists, they love to do the resistance measurements, but they were interested in resistance measurements down to atomic level. They were looking at certain vortex structures and certain finer structures on the surfaces to look at the origin of superconducting behavior. For example, suppose you want to image normal and superconducting states. So you would like to see the domains, finer domains, smaller domains where normal states are there and superconducting. So that was a driving force. But there was no instrument. So they thought physicists, they start building their own instrument. That is the first thing PhD students in physics should do. Ideally, they should make their own instrument. So then came they experimented with the tunneling, which is a quantum phenomena. You know that. So they, by maneuvering a sharp metal conducting tip over the surface of sample at an extremely small distance. As I mentioned that some of these technologies were available with the physicists, the ideas were available. So Binning and Rohrer found that amount of electrical current flowing between the tip and sample could be measured. And once they started measuring it, then when they plotted it, so then they found it shows some kind of a three-dimensional atomic scale map of the sample surface. So in 1979, January, they submitted first patent disclosure from the IBM side discussing scanning tunneling. microscope. Then third scientist joined hand, Gerber. He had a tremendous, and there was fourth one, Quit. These four people contributed a lot for development of later on even down to the atomic force microscope. So this Bening, Rohrer, Gerber, and Quaid, they were early 4 or 5 people who really uh, developed this. Of course, Nobel Prize was given to only two of them, but the contribution was, immense by other two people also. So their first experiment involved the surface structure of gold, and that started showing rows of precisely spaced atoms and broad terraces separated by steps, 1 atom in height. So they could see the terraces, they could see the precisely spaced atoms. So that was never seen by humankind in the history of the humankind. That was never seen actually. So that was actually Nobel Prize. Like in Bening's his own word in the Nobel lecture, I could not stop looking at the images. So that kind of excitement they themselves had about their own invention. It was like entering into a new world at that atomic dimension, that you can see those things actually. You can see the terraces of atomic layers when one layer ends and another layer starts. Uh, I put this note just 15 minutes back. This very fresh note. So you might be wondering what was going on with electron microscope at that time. Electron microscope scopes were still struggling with the problem of aberration, spherical aberration, chromatic aberration, because electron sources were not very perfect and lenses had a lot of imperfection. So biologists were excited. Biologists got a lot of Nobel prizes by that time using electron microscope. Please note that a lot of Nobel prizes in structural biology. I would say in Hindi that biology वाले धड़ाधड़ Nobel Prize निकाल रहे थे उससे इलेक्ट्रॉन माइक्रोस्कोप से, because उनको जरूरत नहीं थी एटम वेटम देखने की. बायोलॉजी वालों को एटम को देखने का क्या करना है ना, उनको इंटरेस्ट नहीं था. उनको तो एक ऑर्गेनेल मिल जाए, कुछ अंदर से सेल में, माइक्रोन साइज के सेल में अंदर से कुछ दिख जाए, दे विल वेरी हैप्पी. So they were very happy, biologists. Okay, ये हमारी तो लॉटरी खुल गई है. But physicists say, oh, it's boring actually. For physicists, it was not very interesting thing. And even for metallurgists, actually, unless you show the atom, I will be interested. Otherwise, I'm not interested actually looking at certain structures which. So electron microscopy was not very, I would say that not very exciting at that time. Of course, today the story is different. You know that already we have 2 Nobel Prizes and one Kavli Prize electron microscopy got a few days back. That is the highest prize in nanotechnology for aberration correction, corrected microscope. I hope you know the news. So that means you have realized already Feynman's dream that STM was able to push and pull individual atoms around, and it also marked the first time that human could manipulate objects that small. Forget about just imaging. So this is the first current profile. This is the displacement. X-axis is basically displacement of tungsten tip. And this is the current in amperes. You can see that it's 10 to the power. This is resistance. This is resistance, sorry, in ohms. It's quite high, 10 to the power 5, 6, 7, 8. And here they plotted current 10 to the power, like it's a microampere and nanoampere. Okay, so this was the small STM. You can see that in comparison to electron microscope, the physics is much simpler. It's so small actually. You can put it on your fist. Of course, electronics was quite cumbersome that time. Now electronics is much better, but the basic design has not changed, and resolution limit of STM. I'm not talking about AFM. I'm talking about STM. STM resolution has not improved, and it should not improve because STM resolution is limited fundamentally by quantum mechanics. Only last few atoms participate into tunneling. So even if you take a blunt tip, it doesn't matter in STM. In AFM, it does matter because you are playing with van der Waals interaction. I'll teach you when we go deeper. that what is the fundamental difference between STM resolution and AFM resolution. I can tell you already that if you think quantum tunneling experiment, even if you take a blunt tip, even if you take something like this pen and like this, so if you keep on zooming, you will see that there are finer and finer structures. So tunneling is so sensitive to the distances that tunneling cannot happen from the areas which are slightly far from the surface. Okay, tunneling will look only see electron conduction pathways. Tunneling pathways will find always shortest path. Got it? Tunneling will always find automatically the shortest path of flow of for the flow of electrons. They will just ignore. They will not flow. Why would they flow from the areas which are far away? So that current will be very small. So that is the trick. Please note that. That is a trick that it automatically limits the problem which was encountered by other form of microscopy. So you have the atomic resolution which is given to you by the quantum mechanics. Laws of quantum mechanics give you the resolution. Okay. So this was second generation of STM with eddy current damping system using samarium cobalt hard magnets. And this was the image of silicon 111 7x7 surface. It was produced in 1982. And this was the world's first images, one of the first for individual surface atoms, and the bonds that could hold them in place were produced by STM. I think some student was asking question about this. I think Sarvani was asking, she's a chemistry student from University of Hyderabad. Okay, so she wanted me to teach also that subject, STM. I normally do not teach that subject to chemistry students at NCL. I taught for, I think, 4 or 5 years back, but then I realized that there may not be that much of interest. So if there is interest, I can give extra classes on scanning tunneling microscopy. I'm just going to give brief outline about STM. I will not going to go deep unless somebody requests me. I have the slides, lectures ready. I think there are 2 lectures only, not more than 2. So yes. So another sample which was imaged, obviously all of you are also scientists, that HPG, highly oriented pyrolytic graphite, HPG is the favorite of such people, including me. If you want to do atomic force microscopy or STM, one of the first surfaces people pick up is HPG because there are less chances of contamination. You can peel it off and you can top layer and you can get fresh layer which is atomically smooth. I already explained what you mean by atomically smooth last time, and what I explained what you mean by optically smooth. So this was 6-volt symmetry in HPG, and one of my biology students, when I started my group, Ramya, she produced similar images. She was not a physicist, neither chemist, and those images are, I think, available. I think I dumped them on my webpage, INCL webpage, and that's what this icon people were also looking at. That those images are wonderful. Yes, and that microscope is currently down. It is one of the world wonderful microscope. Still it is so powerful that it can beat the best of the microscope. Though it is almost 17-year-old, but amazing microscope. Unfortunately, it is down because of some small issue. Okay, so AFM. Now we come to the AFM. Okay, so patent was filed in 1979, but formally it was announced that AFM invention itself is announced in 1981. I think so. Yes, 81. Yes, 79. It doesn't matter actually. It hardly matters. 79 or 81, but around that time. So second, So immediately after that, the birth of AFM happened, atomic force microscope. Now it sounds very trivial that, oh, okay, AFM, what is big deal? But just think about AFM. AFM idea was, there was no as such precursor or predecessor for AFM. Obviously, you can say that, okay, STM is a predecessor, but physics is completely different. Physics is completely different. There's no match. There is, I mean, it was, I would say that it was a completely mind-boggling idea. It was a completely out of the box idea. Transition from STM and AFM would not have been so obvious. So I'll tell you a small story actually. What how it happened actually. The same person started. So he was frustrated probably that in order to image materials, you have to take the materials. They are those are electrically conducting, and so STM was basically like father instrument. You can say that it gave rise to whole family of related instrument technique, and it is never ending. As of today, STM is family of STM is growing, growing, growing like anything. You know, the STM, the technologies which were there in STM were used to branch out like anything, and so he was basically Beanie got the idea of AFM in 1985, 1 year before he got the Nobel Prize for STM, when he was in California. So he was on a leave from IBM Zurich, Switzerland. So he was invited by California, Stanford University, and IBM also has its own research center, IBM Almaty Research Center in US. So he was on sabbatical, and he had more he found more time to think. You can see that when you are away from laboratory, you get more time to think away from the chaos. So he was lying in his apartment, and he was looking at the ceiling of the apartment. Okay, and and then he was thinking, and then it seems that inspiration came from. It's very important for students like you know how he got inspired to develop the AFM, that he was staring at the ceiling, and then he looked at all kinds of structures. You think about yourself when you are not getting sleep, and you are lying in the bed. You start looking at all kinds of structures at the ceiling and all kinds of things, okay, for several minutes. So that reminded that can't we get this kind of a topography in STM? What's the problem? So then he said that why do I need to use current to image the surfaces? Why I can't use force? So this was the trigger. Why not force? Why current? Please note that. Then he did some calculations with his fourth colleague, all these two colleagues actually, Gerber and Kuwait. They were Americans. They were at the so Gerber was a scientist at IBM American Center, that Almaty Center, and Calvin Kuwait was a professor at Stanford. I think the AFM lecture earlier, he mentioned that Kuwait later on he developed AFM, a separate AFM. That is another story, and that became now Park and other things. Park also worked there with Kuwait, and okay, so they built later on their own variations of AFM and something like that. So then when he discussed these ideas with these two people, okay, and so Rohrer had nothing to do with that. Rohrer was still there in Europe, Switzerland, okay. So Beenig went to US in 1984, 1985, and then he discussed that idea with Gerber and Kuwait, and they thought to replace current mapping with the force mapping, and they obviously wanted to look at cantilever with the spring constant weaker than spring constant between atoms, because they didn't want to break the atomic bonds. So the cantilever which was required, I don't know whether you can see this cantilever, uh, okay, probably you can see this is like a cantilever which is moving and like it's oscillating. Okay, so it was. it should be weaker than the okay. So you can do simple calculation. Many of you are chemists, you know the spring constant, you know the frequency from IR measurements, so you can back calculate the k has to be calculated. Mass you know already of atoms, so if you put the mass of atoms around 10 to the power minus 25, and mm, and if you take a molecular frequency around 10 terahertz or higher, whatever you want, so that gives you spring constant around 10 Newton per meter. And for comparison, if you take household aluminum foil, जो kitchen में होती है, and if you take 4 millimeter by 1 millimeter aluminum foil, and if you make cantilever out of that, that spring constant is much weaker. That means there is no reason to worry. So you can safely make cantilever like this. So you have this kind of a cantilever, and then this is the tip. So they set out to start making this kind of a cantilever spring, which could be able to use the subtle forces. And the force, this formula came from Hooke's law: F is equal to minus kx. That's it. So force is proportional to the spring constant and also displacement. So displacement is inversely proportional to spring constant. So lower the spring constant. So lower the spring constant means, say, if I apply, I'll stop sharing and then I will explain you something. And yes. So look at this. Look at this cantilever. So AFM cantilever is like this. Okay. So this is also made of aluminum. One of my students cut it somewhere. I think they got it. No, not my student actually. There is a story behind this. One of my students, Dubai, brought it from, I think, Ahmedabad. I gave a lecture there, and then uh, I think they transported it in some flight or train. I don't remember. So we got it cut from. I don't remember the history of this. I don't have history of this, but I have history of AFM. Okay, how it ended up in my lab. But it is nice to teach actually, and so you can see that you can, if you apply a force on this, okay, like adhesive force, so it bends actually. So if it is softer, so it will bend more with the same force. If it is rigid, then it will not bend that much. So if it is longer, okay, if it is longer, then it will bend more. If it is shorter, it will not bend that much. If I take shorter cantilever, and if I apply same force, it's not bending, right? And if I take longer, and if I say take if I apply same force, it is bending more. Fine. If I take this broader, then it will not bend much. Okay. And so there is a torsional movement also. So there is this kind of a movement, vertical, and there will be this movement. So one student was asking about frictional force microscopy. So frictional force microscopy, you can measure by this kind of a torsional movement. Okay, so this tip can move like this rather than like this. And for example, I'm measuring the topography of my hand. So you can see that on my hand, so I have, okay, this side of the hand. So this side of the hand, you can see that this is a lot of muscles are there or flesh, and this is bony structure, right? Bone. Okay, so the mechanical properties of this and this are different. So if I press my hand, I hope you are able to see. Uh, in the actual class, it is much easier to see these concepts. So if I press somewhere here, so by this tip, so you can see that I'm trying to press, okay, either, so this is the tip or cantilever, and then there is this is basically the tip of the cantilever. So we call whole thing as a tip, but it is cantilever and tip. So if you press it on the hard surface, you can see that it can't compress this hard surface because its mechanical properties are rigid. Okay, uh, so if I press this more, so this tip will bend in certain direction. I can measure it, and if it is soft, and then uh, the deflection doesn't happen that much. So in principle, by this deflection sensitivity of the force, I can measure basically the force itself. If I know the K, if I know the spring constant, and I know the deflection, so this is deflection, this dimension, how much it deflects. Okay, I can measure this side. Okay, and I already know the K of this, so I have the force. That's it. So I can do the force mapping. I can do the adhesive mapping. I can measure all kinds of forces, and I can also, if I tell my microscope that I want to keep my cantilever uh, at a fixed distance from the surface, and my hand is bumpy, so okay, it is not uniform. So if I'm moving this tip over the surface, you can see that once I move this tip over the surface, because topography is different, so amount of force will be different because distance is changing between this surface and this surface. So that leads to the force variation, and then we can pick it up because this guy will pick it up, any variation in the forces. So in principle, so that was the reason that they could measure the forces. Those scientists could measure the forces. Right now, this will excite that student Sarvani that it is possible, because that was precisely her question, that whether you can image the uh, rings, carbon benzene rings. So STM definitely can do that, but AFM can also do that as well. Okay, so so in 1986, finally, they declared the first AFM, which was called as contact mode AFM. So in contact mode AFM, as I showed you, that the tip is always in the contact regime of the force spectrum. So what do you mean by contact? Already you are aware of that. If you are not aware of that, I will teach you in a nice way. But when I say how do we scientifically validate that it was in the contact mode? So when you start actually, if you look at the Lennard-Jones potential curve, you know that the curve, how the curve looks like. So as soon as you start feeling the upturn of the Lennard-Jones potential curve, so that means you start feeling slightly the repulsive forces. So when you start feeling the repulsive forces, that means you're in the contact. Okay, unless you don't feel the repulsive part of the curve, that means you have to bring cantilever closer to the surface even more. Uh, until then, you can't say that you're in the contact. So that means you're all, that is called touching actually, or contact in a layman term. So contact is not a scientific term. Please note that. Okay, as I mentioned that smoothness is not a scientific term. Roughness is not a.
Oh,
Hello.
yes, sir. Sir, I have a question, sir. Can I ask?
Yes, yes, yes.
Yes, sir. Actually, as we know that that tape is actually measuring the area which is around few nanometers. I mean, 100 nanometer, 50 nanometer. So how they are preparing such small tip, and they attached it to with the attached it to the
Good,
cantilever.
good
I
question.
mean,
Yeah. So
uh,
Rizwana's mind is working super fast. Okay, good question. It's a curious mind. So I hope you should all ask these questions. So she's asking that, okay, Rizwana is asking that, okay, I want to make AFM at my house because I'm sitting idle. So how can I I have made all the entire AFM, but I'm not able to make it. Probably she's doing that. Rijwana, are you making AFM in your backyard?
No, no, sir, but I just
No, when I joke, I am not basically. It's not a joke actually. It's a reality. People are. You can buy kits on Amazon, and you can make your own AFM. It's not complicated. So coming
sir,
to
and it is also very much required in India also.
actually, there are a lot of efforts on India-made AFM. India's first STM was made by Professor Arup Rai Chaudhary and at Indian Institute of Science. It was made quite early, actually, in 90s. Yes, early 90s. They didn't wait for a long time. And AFM was first India's first AFM was made right here in Pune University. If some people are there in my lecture from Pune University, so they should feel proud about that. Okay,
So,
so
but why people are buying this not from India?
which one we don't.
Our institute also bought it.
Yeah, you're right. So there is I think I wrote an article on Facebook, and there were a lot of reactions on that. I'm part of that committee actually, international committee now. Even my students do not know about that committee which I'm part of. So basically, there are many problems when for example, suppose you have made the AFM. So how will you commercialize it? Do, that's the problem. You can make AFM, but commercialization takes. Uh, so basically, you are a hardcore physicist. You have been always in the laboratory with the books and with the material synthesis. You made AFM, but this entire process, Rijwana, is so exhausting. Rijwana, right? Especially in the Indian condition, that students or scientists they get so exhausted by making those instruments because it's not easy to resource. As you've already mentioned, that how will I make tip and there are so many things actually. How will you get the piezo? Piezo you can't make yourself for movement of the tip. So you have to source small components from here and there. And I have made. You can ask this question to me also. I made magnetometer. India's first magnetometer was made by me actually at JU in my PhD. So how I could not commercialize it even today? It's not commercialized. So commercialization, number one problem is that Indians don't have the entrepreneur skills. We make something to use it in the lab, and we publish the paper, and then we finish the PhD, and then we look at the safe, secured career option. We need to worry about our bread and butter to feed our family. Forget about entrepreneurship, because if it doesn't sell, and it doesn't sell actually, because how will you calibrate it so precisely, and how will you make every piece? So who will fund your entrepreneurship? Actually, there was no funding. Now there is a concept of funding. Startups are there, but that time there were no startups. So they are not at all blamed. Nobody is actually blamed. The environment was not there. Even today, the environment is not there. For example, you have made the AFM today. इवन टुडे रिजवाना यू विल फाइंड एडी चियोटी का जोर लगाना पड़ेगा तुम्हें अपना एफएम बेचने के लिए. वो आलू प्याज टाइप से नहीं है कि इवन तुम आलू के चिप्स बनाना चाहोगे ना तो तुम्हें नानी याद आ जाएगी रिजवाना वो बेचने के लिए. फॉरगेट अबाउट एफ.
Industrial collaboration is very less.
No, actually, it's not. Yeah, we don't care about. So another problem is that we don't have standards. For example, forget about making the AFM. For example, you buy the AFM. The article was basically that suppose you want to reject a tender of China, and you have your technical quotation. So how will you do that? Do you have your standards? Suppose you want to measure some distance. I mentioned about that in my earlier lecture. That how will you prove that this distance actually? It's not that easy actually. Even today, it's not easy. So most of the scientists they are not successful in India. I shared that article also written at medium.com by Professor Subhash Kar, that what is the problem that same people, same scientists, if they are put into some other environment, for example, US or Europe, they are successful there, same people. But in Indian environment, same genes, same people are not successful. It's a problem here quite a lot. So let us not go into that, but salute to those Indian physicists. At least they made it actually. That is quite a lot. They could not commercialize it, but their AFMs produce world-class students and papers and stuff like that. I really do not blame any of my um, those seniors who could not do that, because I myself I am aware of the problems. Let us. So this was one of the first image of AFM, which was built by Binning Quid. And please remember, this effort was from IBM, one of the top technology company of that time and even today. And another university involved was one of the leading private universities, Stanford. So they had unlimited funds. They don't need to worry about any, if scientists want some component, IBM will source it from any planet, any part of the planet actually. No problem with the money. They will be given unlimited money. Here, even students are troubled by utilization certificates and other things they have to submit. So you can't get Nobel Prize from DST projects actually, pre-year DST project. Forget about that, because you will be busy in getting the next funding. I think you know what I'm telling you, right? So forget about yes. Afternoon,
No,
yes.
sir, please go ahead. Yes.
Yeah, yeah. So I had to some PhD I was there in afternoon. So okay, so you can see that. So this is distance. X-axis is distance, and this is lateral distance, XY distance, and you can see that this is Z-axis, and this is already in angstrom. So this was amazing because you can image all kinds of surfaces, non-conducting, conducting, using as simple as van der Waals force. So this was a design of first AFM. It is kept in the Science Museum, London. If you go to London, you must visit to Science Museum, and you will really find in the science section, in the section there somewhere in Microscopy, you will find this. So this was, again, you can see that HPG is very lucrative surface. Everybody would like to probe. And this was from AFM. I already showed you HPG image from STM. And but people were still not happy. I told you the precursor was STM. STM was basically like a father figure of that instrument family, and then came AFM, which worked in the contact mode, and then it started like all host of, and people started developing all kinds of things actually. Then immediately after 1 year came the invention of non-contact AFM, that okay, you don't need to be in the contact mode because tip is indeed prone to scratching the surfaces. So you can be in the non-contact mode, and it's not trivial to keep the tip all the time in the non-contact mode. Please remember that there are strong adhesive forces which are acting, and those forces will try to pull the tip down to the substrate. So you have to counter those forces and fly at certain nanometer, few tens of nanometer away from the surface. But it is not a joke, because you are in the strong. Please remember again the Lennard-Jones curve. I should have put the curve here so you remember. So we are in the strongly attractive zone here. And another problem with AFM, see, STM, you can calibrate very easily the Z distance, because you know how the current falls with distance. I is exponentially dependent on Z and KVT, Arrhenius law. So you can calibrate the Z very easily. But force, you know that force is very complex. You already know the Hamaker constant and Z. R square, it falls by R square and all kinds of things. It depends upon the geometry of the tip and sample. So that is very non-linear. It's not a linear zone. So that's a problem, that as a function of Z, which is out of the plane direction, it is not very easy to calibrate the forces. Unlike we will discuss about that when we come to the calibration part. So this was amazing that how do you, because it was important for polymer samples and soft biological samples here to get rid of those strong forces, adhesive forces, including capillary forces. So what they did that they were actually oscillating this tip at small distance, okay, rather than tip moving like this. So they were oscillating. So suppose it comes into the so basically one advantage is that you are always taking derivative of the force. So basically you are doing force mapping also. That detail I will tell you later on when we discuss this more in detail. But this is just history part. So this was invented by Professor Vikramasinghe. He published Journal of Applied Physics in 1987. Probably Sri Lankan American Martin and Vikram. I've read this paper many times. It's an impressive work. And yes, this is the paper. When I say that this impressive paper, that means I've read it and see the photograph. Sometimes I'm not aware of because so many slides, so I'm not aware of. So you can see that, and Professor Vikram Singhe has cited this book, which I also like. This book, this is the first reference he has cited, and this is the first book which I always recommend: Intermolecular and Surface Forces by Jacob Israelechvili. Israelechvili, yes, and you can see that second paper probably will to be published. It is written here, but Journal of Colloidal and Interface Science. So you can see that this is actually a colloidal chemistry work, and then he has cited Binning and Rohrer, Scientific American, and again Binning and Rohrer work. So this was amazing. This here, it's very useful for me to teach you. So you can see that this blue shaded region is where contact AFM works. So you are already in the repulsive zone. So contact AFM means contact is not a scientific term. Again, I'm telling you. How do you please, you should be able to tell the people now that what do you mean by contact? Contact means the repulsive force region, Pauli exclusion principle. Okay, and I already told you by the example of holding your own hand. Okay, so you can say that, okay, now you are in the non-contact and now you are in the contact region. And another example, when you eat a bowl full of noodles, then I'll give you that simple example maybe in the next class. That is amazing example, and I just out of blue I started using that example, and student liked it because most of them, they love noodles. So that example I'll teach you later on. So this is hardcore scientific example that this is contact region, and this is green region is non-contact. You can see that, and this is highly non-linear. So you can see that force is dropping very fast as a function of distance. So that means AFM tip is highly sensitive to the Z distance. It is in sub-angstrom. That's where the sub-angstrom vertical resolution comes. So there are two resolutions in force microscopy: lateral and vertical resolution. So this vertical resolution is so amazing because of this sharp change in the force when you do a small change in the distance. Similarly here, it is not as sharp here if you do the non-contact mode AFM. So the change is not that sharp, but you are now in the attractive region. Got it? So now you can say that what do you mean by contact? Contact means that top layers of atoms from both the objects are in the repulsive region. It's not possible for them to crash any further. So that is the actual meaning of touch. So then there were problems with non-contact AFM also, and you had.
Sir, in our previous lecture of AFM, that the person who was given, that he said that non-contact mode is always useful and more useful nowadays. But as you have shown that non-contact mode is less, it will give us less
See,
idea about
it is
since it is
business.
public.
It is more business of park systems. That's why when I will come to that. I have slides on park system. So park system started I'll tell you what is the scientific reason of his claim. His claim is correct that non-contact AFM is got more popular, and it was popularized by his company Park Systems. And but it doesn't mean that all the instrument, for example the system which I had almost for 15 years, it doesn't have the non-contact mode. It doesn't have that electronics to control over that distance. But it doesn't mean that you can, and he himself in a private conversation with me, he called me and he said, "Oh, sir, which microscope you have?" I said, "That microscope." He said, "That microscope is better than Park system." Okay, so these are actually, that's why you should not take too much, because that is a business talk, that is a commercial talk. Okay, so, and you are a scientist, Rijwana, so we have to validate that on scientific claim, and that is precisely your question. That your question is very scientific. That, oh, that guy claimed that non-contact is better. I will tell you in the next lecture how his claim is good, and I'm not denying that his claim is not. But there are technological problems in making the non-contact AFM. It's not as easy. So these days we have very good non-contact AFM in the market. So it didn't come to the market. It was not a main place for the market. I'll come to that. I'll answer your question when we teach. I'll be teaching non-contact AFM. So on contact, there were a lot of difficulties, as you can see that, as I mentioned, that it was not easy to keep that tips balanced in that region because of the strong attractive forces. So then they realized very soon that non-contact is not a very practical mode. At that time, I'm telling you, not today. Today we have much better control. So then they invented tapping mode. Tapping mode became instantly popular, and even today it is the most popular mode. Tapping mode is very popular, and it basically breaks free of strong adhesive forces. Suppose your sample is very sticky, so then it can break free of strong adhesive forces. So basically, tip doesn't remain in the. So what basically happens that in tapping mode, you are alternatively in the contact mode and you go to the non-contact mode. So for a very brief time, you are touching the surface. You know what I mean by touching. So you are going from repulsive region to uh, attractive region, and in 1 second you are doing that probably 1 million times. The frequency is almost 100 kilohertz. 100 kilohertz is already not 1 million times, 100,000 times, 100,000 times. ठीक है, 1 लाख हिंदी में बोले तो 1 लाख 2 लाख इस टाइप का 1 सेकंड में टिप इतनी बार टच कर रही है ना, 1 लाख टाइम, ओके, 2 लाख टाइम और समथिंग लाइक दैट. So that means you are probing that gently. You're tapping the surface. You're not like scratching it, and neither you are completely away from the surface like you are here in the non-contact mode. Nor you are always in the scratching mode that you are scratching the tip here. You are always scratching. Okay, so you are somewhere in the middle, and for that constant tip has to be constantly. And another advantage is that here you can break free because the force is so high that you can break free of any strong capillary forces. So that was a very neat thing actually. Just a moment, let me go back. Yes, so if tip makes an accidental contact with the sample, so that was a problem, Rijwana, that in non-contact mode, but the problem is that, okay, you have to always maintain a certain specific distance, few nanometer, and it is very, very difficult actually using, it's electronics nightmare, and it's not possible for all surfaces. And to prevent the tip from contacting the surface, that was a problem with non-contact. And if tip makes accidental contact with the sample, it can stick to the sample surface and stop vibrating due to the meniscus force of the liquid layer and surface sample surface. So therefore, a very high performing Z servo, now the answer is here, what I've been telling. So you need, it's an electronics problem. You need a very high performing Z servo motor is required for non-contact. So that makes the electronics very expensive. And another problem is that mechanical response has to be very fast. So the scanner has, so that is very, it's not required also. Then to solve this problem, Zhong et al. Introduced a tapping mode in 1993, imaging in which a tip strikes against the surface of on each oscillation cycle and detaches also. So basically, you are looking at all the properties. So you are looking at mechanical properties. Another disadvantage of non-contact probe is that you are not touching the surface. See, when you touch the surface, without touching the surface, you cannot get the mechanical properties. ठीक है? अपने सिर पे हाथ लेके जाओ और अपने सिर को दबाओ एक उंगली से, है ना? सिर हार्ड है या सॉफ्ट है, कैसे मालूम पड़ेगा जब तक टच नहीं करोगे आपका सिर, है ना? लाइक दिस, ऐसे थोड़ी ऊपर से आप चले जाओ बोलो कि हाँ मेरा सर मतलब ऐसा है, हार्ड है एकदम बजाने में, हाँ. So that was another limitation, that non-contact cannot give you mechanical properties in the same experiment, which is possible in non-contact. So you are touching the surface so many times. Okay. So then this paper came actually in 1993 by Zhong and Zhong et al. And they say that polymer and silica fiber surface is studied by tapping mode AFM. So that was actually done by, you can see, it's very interesting. The affiliation, AT&T Bell Labs, now you know that it is closed down long back. We don't have, unfortunately, we don't have Bell Labs now at Murray Hill, New Jersey. And let me tell you, this patent was taken by Digital Instrument. Digital Instrument is actually the original manufacturer. Name has changed now. After that, it was sold. This company was sold to Vico Instrument, and Vico's Instrument sold that company to Bruker. So this is now Bruker actually. So, but this is the original company which held the patent actually for tapping mode AFM. So no other company could use the same term. So don't get confused if some other company says sell the same mode by some other name, because tapping mode is patented technology. Okay, so this is called. So you can see that amplitude here is 100 nanometer in tapping mode, because it has to tap and break free of those forces. So amplitude is quite large here, and here amplitude is around 1 nanometer, and it just flies over the surface. And if there is any strong capillary forces, so it will get stuck. तो हो गया इसका बेड़ा गर्क है ना, ये प्रॉब्लम है इसमें. So you can see that so this image is basically from Park AFM. I have put it actually. It supports the claim of that person. But I told you the problems also, that I mean, I do not know. I didn't check this. This is from their website. But I'm showing you, you have to judge yourself, because I have not checked their AFM. I have not used their AFM, this technique, because usually Park people, they love to, they show it actually that they are better than the tapping mode, slightly better. This is the tapping mode image for the same area, and this is what they call it actually true non-contact, right? वो बर्तन मांजने वाले जो डिश पाउडर होते हैं ना, वो कहते हैं मेरा पाउडर ज्यादा अच्छी बर्तन चमकाता है, तुम्हारा कम चमकाता है, तो वही वाला प्रॉब्लम है यहाँ पे. So this is the design, and it is the same design. So this is the scanner. So you can either scan the tip. Either tip can move and sample remains same stable, or sample can move and tip can remain. Tip can move or sample can move. In this case, you can see that there are X and Y is Z controllers, piezo driver. They supply the voltage, and this is the piezo tube. So by applying the voltage, you can move in X direction, Y direction, and Z direction. Tip remains wherever it is. Only it has got this torsional movement and lateral movement and all kinds of up and down movement. And those movements are read by this laser diode. This is a split photo diode. This is split in 4 parts. Here it is. Here the 2 parts are shown, but actually there are 4 parts. I'll show you why we need 4 parts. 4 parts are needed when you would like to use the frictional force microscopy also. If you do not want frictional force microscopy, you can use 2 parts. So suppose you want to catch the data of, then you need actually two, what you call it, lock-in amplifiers, 2 lock-in amplifiers. So this is the electronics of that, and this is a PID controller, proportional, integral, and differential. And so you detect the amplitude, and then basically then you feedback. This is a feedback loop. You feedback basically, for example, you have to maintain certain distance of the tip over this surface, and so suppose it came over certain higher object, so tip will deflect higher about in the repulsive region, and this will be picked up, and the signal will be fed. Oh, you are flying high, come down, or come up, come up. So for example, whatever. So this controls the control this scanner. So it will move the scanner down so that you are flying in the safe distance. So if you understand this graph, this schematic, you understand the brain of AFM or STM, even STM also. All kinds of force macroscopies is based on they are based on this basic electronics. There is no change. This is a very simple electronics. I'll teach you this later on. So then came another demand 1 year later that, okay, the tapping mode looks fine, looks wonderful, and it's much easier than tapping mode, and it's much easier than the contact mode and non-contact mode. What about next demand that, okay, I have biological cells or some of the wet polymers, can I do AFM in fluids? Then this mode came by Paul Huntsma's lab, and again he wrote several Nature articles. Quite a lot of work came from Huntsma's lab. If you go to his website, just type Huntsma lab, and all kinds of papers are there. And I don't know whether still, I think it's still there, but I'm not sure. I can confirm. So then they developed a fluid cell in my own lab. My earlier students, Ramya, Umesh, Imran, they did a lot of work with this setup, fluid cell. And by accident, some student ended up leaking the water from this cell, and this water entered into this scanner. And this scanner is piece of very expensive electronics, around $4,000 at that time. So that got damaged, and I had to ship it to US. So because in our AFM, entire electronics was in the scanner part. So scanner was very, it was held at high voltage. So somewhat water, if it leaks, then it will penetrate here and it will short this scanner. So for biological experiment, usually what they do, they put electronics at the tip side. So the tip moves, not the scanner. So even if the water leaks, then there is no problem. So, and also for biological instruments, it is easier if you move the tip, because you can make large amount of samples. So suppose you are moving the sample. So in our instrument, you cannot you cannot put larger samples. But the advantage of, I will teach you that part also, that if suppose you have to buy the instrument, so which one you buy. So, this instrument which we have gives you much higher resolution when you move the sample than moving the tip. Yes, but the disadvantage is that if you try to do this fluid cell measurements, any fluid leaking can destroy the scanner there. So again, this was the original paper in 1994, Paul Huntsma's lab in California, Santa Barbara. And it was in collaboration with again, Digital Instrument, the first commercially, I think they were the first company which commercialized the AFM. So you can see that 70 kilohertz in this case, tapping mode, and they were able to do they were able to produce the first images of DNA. So you can see that these are the images of DNA as early as 1994. These are all. So Paul Huntsma had a lot of work on the DNA imaging. You can see that from physics lab, he was giving a lot of contribution in the structural biology. So finally, then you could see that you can image mammalian cells or bacterial cells. So this is basically a nucleus of the cell, and these are organelles, and these are some biopolymers, phospholipid, and all kinds of lipids are there, proteins are there. Okay, receptors are there at the cell surfaces. Cell surfaces, you know that there are a lot of things, all kinds of receptors are there. Hello, hello, hi Prasad, hi. Ha 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 ha. Uh-huh. One I put there, I think. Oh, is it? Oh, okay. Put one or two, whatever. It doesn't matter actually. Yeah, yeah, it's fine. It's fine. It's fine actually. Yeah, yeah, no problem. Okay, I'm teaching actually. Yeah. Okay. Yeah, thanks. So this is the end of the today's lecture, and I hope that you like this beautiful journey. I really like this uh, this entire thing.